That starry sky is a grand illusion of completeness. We have charted countless suns and galaxies, but our deepest telescopes eventually hit a wall, a fundamental limit to what we can ever see. This boundary is the edge of the observable universe, a horizon created by the age of the cosmos and the ultimate speed limit of light itself. By the end of our journey, you will understand not just where this edge is, but why its existence forces us to reconsider everything we know about reality. We will explore what might lie in the infinite darkness beyond our view, and grapple with the possibility that most of the cosmos is forever hidden from us. How does it feel to know there is a frontier we can never cross? Our cosmic address is not a fixed point on some grand map, but a sphere of visibility, a bubble of information centered right here on Earth. Its radius is a staggering 46.5 billion light-years. Now, that number seems to contradict itself. If the universe is only 13.8 billion years old, how can we see something 46 billion light-years away? This is the central paradox of our cosmic horizon. The light from the most distant galaxies has been traveling for almost the entire age of the cosmos to reach us. But during that immense journey, space itself has been stretching, carrying those galaxies even farther away. The object whose light we see today from 13 billion years ago is now much, much farther off. This boundary, the particle horizon, marks the absolute limit of any signal that could have possibly reached us. It is the ultimate travel log of light. But there is another, more subtle horizon, the cosmological horizon. This defines the future limit of what we will ever see. As the universe continues to expand at an accelerating rate, distant galaxies will eventually be carried away so fast that their light can no longer make progress against the stretching of space. They will fade from view one by one, their light redshifted into oblivion. This means our observable universe is not only finite but actually shrinking in terms of the number of galaxies we can one day detect. We are forever trapped within this sphere of the knowable, a cage built from the speed of light and the expansion of space. It is a profound and humbling realization that there is a fundamental limit to what we can ever know, a wall built into the very laws of physics. And it forces a single, inevitable question. If this is all we can see, what lies in the infinite darkness beyond the reach of our deepest telescopes? This speed limit, the velocity of light, is a fundamental rule written into the fabric of space and time. It dictates that nothing can travel faster, making light our only cosmic messenger. But this same messenger is also our jailer. Every time we gaze at a star, we are not seeing it as it is now. We are looking at a delayed broadcast, an image from the past. The light from our own sun takes 8 minutes to reach us, so we see it as it was 8 minutes ago. Look at the Andromeda galaxy, and you are peering 2.5 million years into the past. This is the price of cosmic observation. We can never see the universe as it is, only as it was. The situation becomes far more extreme at the very edges of our vision. There, we see galaxies as they were just after the Big Bang. But here is the truly counterintuitive part, the consequence of dark energy's relentless push. The space between us and those incredibly distant galaxies is expanding so quickly that the galaxies themselves are being carried away from us faster than the speed of light. Think of it like a runner on a moving walkway that is stretching faster than they can run. Even though the runner is moving forward, the stretching of the walkway carries them backward, away from the finish line. In our cosmic analogy, the runner is a beam of light, and the finish line is our telescope. For galaxies beyond a certain critical distance, their light is fighting a losing battle. It is traveling toward us at light speed, but the space it must cross is widening so rapidly that the beam makes no net progress. That light will simply never arrive. Those regions of the cosmos are forever placed beyond our observational grasp. not because they do not exist, but because the universe itself has erected an impenetrable barrier between us. This is not a violation of Einstein's laws, where nothing can move through space faster than light. This is space itself expanding, carrying galaxies along for the ride, and it can indeed exceed light speed. This reality, confirmed by our measurements of dark energy, means our island of visibility has a hard shore. We are surrounded by an ocean of unreachable cosmos, a vast darkness that we can infer but will never directly witness. What wonders, what entirely different configurations of matter and energy might exist in that infinite exterior? The answer is locked away, not by technology, but by the fundamental rules of reality. The very laws that built our cosmic cage also hint at a reality far grander than we can perceive. To truly grasp the nature of this horizon, we must journey back to the universe's very first moment, a time of almost unimaginable energy. In the tiniest fraction of a second after the Big Bang, the cosmos is thought to have undergone a spectacular transformation known as cosmic inflation. Picture a single subatomic particle, smaller than anything we can measure, suddenly exploding into a volume larger than our entire observable universe, all within a span of time so brief it defies analogy. This was not a violent explosion into space, but a hyper-fast stretching of space itself, smoothing the infant cosmos into the remarkably uniform fabric we detect in the cosmic microwave background. This afterglow of creation appears almost identical in every direction we look, a fact that inflation elegantly explains. It tells us that regions of space now on opposite sides of the sky, separated by tens of billions of light years, were once neighbors, close enough to exchange energy and reach a common temperature before being ripped apart by this primordial expansion. Yet this solution reveals a staggering implication. If inflation could stretch one tiny patch of space into everything we can see, what stopped it from doing the same elsewhere? The leading theory suggests that inflation is eternal, ending in our patch to form our universe, but continuing forever in the wider cosmos, constantly spawning new universe bubbles. This means our entire observable universe, with its hundreds of billions of galaxies, may be just one island in an infinite archipelago of universes, a multiverse. The edge of our observable universe, then, might not be a true boundary of existence. It could simply be the limit of our local bubble, the edge of our island's light. Beyond it lies not emptiness, but an endless ocean of other universes, forever separated from us by an ever-widening gulf of inflating space. The horizon we face is not the edge of creation, but merely the edge of our sight. This ancient glow, the cosmic microwave background, is our ultimate time capsule. It is the oldest light in existence, a fossilized echo from a time when the universe was a mere 380,000 years old. Before this moment, the cosmos was a searing, opaque fog of plasma, so dense that light particles, photons, were constantly scattered, trapped in a perpetual traffic jam. Then, as the universe expanded and cooled, electrons and protons combined to form the first neutral atoms. Suddenly, the road cleared. Light, for the first time, could travel freely across the universe. That first burst of liberated light is what we detect today as the CMB, stretched and cooled by billions of years of expansion into a faint microwave whisper that permeates all of space. This radiation forms a perfect sphere around us, a literal wall of light at the very edge of our observable universe. It is the final curtain beyond which we cannot see with light, because before that curtain rose, the universe was simply not transparent. Peering at this wall is not like looking at a blank screen, however. It is studded with incredibly subtle imperfections, tiny variations in temperature. These anisotropies are the fingerprints of the universe's infancy, the imprints of quantum fluctuations that were magnified by inflation into the seeds of all future structure. The slightly denser patches revealed in this ancient light would, over eons, collapse under gravity to form the first galaxies and the vast cosmic web we see today. So, while the CMB is a wall blocking our direct view, it is also a profound historical record. But it is still a barrier. To learn what happened in that first fleeting fraction of a second before the light was set free, to peer behind this ultimate curtain, we cannot rely on photons. We must listen instead for the faintest tremors in spacetime itself, the primordial gravitational waves generated by the universe's violent birth. But what if we could find a different kind of messenger, one that was not trapped in that primordial traffic jam? Gravitational waves are ripples in the very fabric of spacetime, generated by the most violent cosmic events. When massive objects like black holes collide, they send tremors through the cosmos, stretching and compressing space itself as the waves pass by. Unlike light, which is easily scattered and absorbed, gravitational waves are incredibly faint and can travel through almost anything. They pass through the densest plasma of the early universe as if it were not even there. This makes them the perfect cosmic archaeologist's tool, capable of carrying information from a time before the universe became transparent. The ultimate prize for scientists would be to detect primordial gravitational waves, the faint echoes generated during the inflationary burst itself. Think of the cosmic microwave background as a photograph of the universe's first birthday. Primordial gravitational waves would be a recording of its first cry, a direct probe of the universe's conditions a mere fraction of a second after it all began. Future observatories like the proposed Laser Interferometer Space Antenna, or LISA, will be sensitive enough to listen for these whispers from the dawn of time. Detecting this signal would be like hearing the echoes of creation, offering us a glimpse behind the ultimate curtain. It would allow us to indirectly observe a realm forever hidden from traditional telescopes, pushing our knowledge of the cosmos back to an era we once thought was completely inaccessible. This would not break the light barrier, but it would cleverly sidestep it, using the fabric of reality itself as a new medium for discovery. Our inability to see beyond the horizon does not mean we are blind to the possibilities. Physics provides us with conceptual tools to build models of the unseeable, frameworks that are mathematically sound even if they are empirically untouchable. One of the most compelling ideas is that of eternal inflation and the resulting multiverse. This theory suggests that the hyper-fast expansion which forged our universe never truly stopped everywhere. Instead, it ended in our local patch, creating the stable bubble of spacetime we inhabit. But beyond our bubble, the inflationary background continues to stretch at an incomprehensible rate. Within that seething, expanding foam, new universe bubbles are constantly popping into existence, each one a separate cosmos with its own unique properties. The fundamental constants we take for granted, like the strength of gravity or the mass of an electron, might be random outcomes in this cosmic lottery. In another bubble universe, gravity could be repulsive or atoms might never form. Our universe is not special, just one possible configuration among an infinite number of others, a single grain of sand on an endless beach we can never visit. A radically different vision is offered by conformal cyclic cosmology. This model proposes that the universe is not linear, with one beginning and one end, but cyclical. In this view, the far future of our universe, a time when all matter has decayed and black holes have evaporated, becomes mathematically identical to the high-energy, ultra-dense state of the Big Bang. The end of one cosmic cycle, or eon, seamlessly transforms into the beginning of the next. The edge of our observable universe in this framework is not a spatial boundary but a temporal one. What lies beyond our horizon in space is, in a profound sense, the future of a previous eon or the past of a next one, a chain of existence stretching infinitely into the past and the future. These are not just wild speculations. They are rigorous extensions of Einstein's theory of general relativity and our understanding of quantum mechanics. They represent our best attempts to follow the cosmic clues to their logical conclusion, even when that conclusion points to realities forever hidden from our direct perception. This pushes science into a deeply philosophical realm. If most of reality is fundamentally unknowable, what is the true nature of scientific inquiry? Are we merely describing our local neighborhood, forever ignorant of the greater continent? These conceptual frontiers force us to confront a deeply unsettling possibility. The existence of a fundamental horizon means that a truly vast portion of the cosmos is, by the unbreakable laws of physics, forever unknowable to us. This is not a temporary limitation of our technology, but a permanent boundary written into the fabric of reality. It forces a profound philosophical shift, challenging one of the foundational ideas of modern astronomy, the Copernican principle. For centuries, we have moved away from the idea that Earth holds a privileged position in the cosmos. But if our entire observable universe is just one isolated bubble in an infinite multiverse, a single island in an endless ocean, does that not, in a strange way, make our island special? It is the only one we can ever know. This isolation creates a new kind of cosmic uniqueness, one defined not by central location, but by absolute informational seclusion. This leads to an even more fundamental epistemological dilemma, a question about the very nature of knowledge itself. Can we truly claim to understand the universe if we are permanently confined to studying a single sample, a tiny fraction of the whole? Science is built on observation, on testing hypotheses against the evidence we can gather. But what if the most important evidence, the data that defines the true nature of reality, lies permanently beyond our grasp? It is as if we were born and will die inside a single, magnificent library. We can study every book on its shelves, learning its rules and its history, but we can never leave to see if there are other libraries, or if ours is just one room in an infinite mansion. Our scientific laws might merely be the local bylaws of our cosmic neighborhood, not universal truths. This does not make our quest for knowledge meaningless, but it does reframe it. We are not mapping the entire continent of existence. We are meticulously charting the island we are stranded on, forever wondering about the shape of the unseen shores. This horizon, then, is not just a limit to our vision, but a mirror reflecting the ultimate limits of human understanding. This accelerating expansion, driven by dark energy, is not a distant phenomenon but a force actively shaping our future view of the cosmos. The horizon we perceive today is not static. It is a shrinking window. As dark energy continues to push the fabric of space apart at an ever-increasing rate, galaxies beyond our local gravitational neighborhood will eventually be swept away by the tide of expansion. One by one, their light will redshift into undetectability, like distant ships disappearing over a curved horizon. Billions of years from now, any astronomers in our local group of galaxies, which is gravitationally bound and will eventually merge into a single large galaxy, will look out into a profoundly empty sky. Their observable universe will contain only the stars of this one merged galaxy. All other island universes will have vanished from sight, their light unable to overcome the cosmic stretch. The evidence for the Big Bang, the cosmic microwave background, will have faded into complete obscurity. For those future beings, the universe will appear as a small, static, and lonely island of stars surrounded by an infinite, black emptiness. They will have no clues to suggest a vast, dynamic cosmic history, no evidence of an expanding universe filled with billions of other galaxies. This paints a deeply isolating future, one where the cosmos itself hides its greatest secrets. This is why the study of dark energy is so urgent. It is not merely an academic curiosity about a mysterious force. It is a race against time to understand the ultimate fate of our cosmic perspective. By deciphering dark energy, we are essentially mapping the future boundaries of our own knowledge, trying to read the final chapters of the cosmic story before the book itself is taken away. This accelerating isolation forces a question that defines the very scale of our reality. Is the universe we inhabit finite, with a definite size, or is it truly infinite, stretching without end? The answer is locked beyond our horizon, but the clues we have point toward a staggering possibility. Our most precise measurements, from observatories like the Planck satellite, reveal that the geometry of the universe is flat to an almost perfect degree. Think of space as a vast, cosmic sheet. A flat geometry means that two parallel laser beams fired across billions of light years will never converge or diverge. They will stay perfectly parallel. This flatness is a critical clue. In an infinite universe, space would be flat, extending forever in all directions. If this is true, then the cosmos does not simply stop at the edge of what we can see. The 46 billion light-year radius of our observable bubble is just the beginning. Beyond that horizon, the universe simply continues, potentially forever, filled with more galaxies, more stars, and possibly endless variations of everything we know. In an infinite cosmos, every possible arrangement of matter must eventually repeat. Somewhere out there, beyond our reach, could be an Earth almost identical to ours, with a version of you making a slightly different choice. The implications are as dizzying as they are profound, but there is another, equally mind-bending alternative. The universe could be finite, yet have no edge. Imagine the surface of a balloon. It has a finite area, but if you were a two-dimensional creature living on that surface, you could travel forever in one direction without ever finding a boundary. Our three-dimensional universe might be analogous to the three-dimensional surface of a four-dimensional sphere. It would be finite in volume, but completely unbounded. In this scenario, if you could build a starship capable of ignoring the expansion of space and travel in a straight line, you would not hit a wall. Instead, after an immense journey, you would eventually return to your starting point from the opposite direction. So which is it? The flat geometry we measure is consistent with both an infinite, flat plane and a finite, but incredibly vast, hypersphere. The difference is in the overall scale. If the universe is curved, the radius of curvature is so immense that it appears flat within our observable patch, just as the ocean appears flat from a small boat. Our telescopes cannot see far enough to detect the gentle curve. Therefore, the true nature of the cosmos, finite or infinite, remains one of the greatest unanswered questions in science. The answer determines whether the reality beyond our view is merely very, very large or truly without end. This cosmic isolation creates a profound puzzle, one that strikes at the very heart of physics. What happens to the information about a galaxy the moment it crosses the cosmological horizon? As that galaxy is carried away by the expansion of space, its light fading from our view, does the knowledge of its existence, its composition, its history, simply vanish from our universe? According to the fundamental rules of quantum mechanics, information cannot be truly destroyed. It might be scrambled, hidden, or transformed, but it must be preserved somewhere in the fabric of reality. Yet, from our perspective, a galaxy that crosses the horizon is gone forever, causally disconnected from us. No signal, no particle, no shred of data can ever cross back over that boundary. This creates a direct conflict, a paradox where the smooth, continuous fabric described by Einstein's general relativity seems to allow for the permanent loss of information, while the discrete, probabilistic world of quantum mechanics forbids it. This dilemma is eerily similar to the famous black hole information paradox. When an object falls into a black hole, it passes through the event horizon and is lost to the outside universe. For decades, physicists debated whether the information about that object was destroyed, violating quantum law. or if it was somehow encoded on the surface of the horizon. The cosmic horizon presents an even grander version of the same problem. Our entire observable universe is surrounded by an event horizon, a point of no return for information. This is not a small-scale anomaly but a fundamental feature of the cosmos. Resolving this tension may require a theory that unites gravity with quantum mechanics, a theory of quantum gravity. Frameworks like string theory or loop quantum gravity attempt to describe the fabric of spacetime not as a smooth continuum, but as something built from discrete, tiny units, perhaps loops or vibrating strings. At this unimaginably small scale, the nature of the cosmic horizon itself might be different. It may not be a sharp, perfect boundary, but a fuzzy, quantum mechanical surface where information is not lost but translated, stored like a hologram on the two-dimensional surface of our cosmic bubble. The edge of the observable universe, then, is far more than a simple limit to our vision. It is a laboratory for the most extreme physics, a place where the deepest laws of reality are put to the ultimate test. Understanding this horizon is not just about mapping the cosmos. It is about deciphering the very rules that allow a cosmos to exist at all. The mathematical parallels are uncanny. A black hole's event horizon and our cosmic horizon are in essence the same type of boundary. Both define a point of no return, a surface beyond which any event, any signal, is forever lost to a given observer. For someone outside a black hole, watching an object cross the event horizon is like watching us witness a galaxy fade beyond our cosmological horizon. The object does not crash into a wall, it simply redshifts into oblivion, its information seemingly erased from our reality. This deep similarity means that the profound puzzles solved and created by black hole physics can shed light on the ultimate fate of our cosmic view. The most revolutionary insight came from Stephen Hawking's work on black hole thermodynamics. He discovered that black holes are not truly black. They emit a faint glow of radiation, now known as Hawking radiation, due to quantum effects at their horizons. This radiation slowly causes the black hole to evaporate over astronomical timescales. But this creates a terrible paradox. If the black hole evaporates completely, what happens to all the information about the stars, planets, and atoms that fell into it? Quantum mechanics insists that information cannot be destroyed. The leading resolution to this black hole information paradox suggests that the information is not lost, but is somehow encoded on the event horizon itself, preserved in a scrambled form and potentially released as the whole evaporates. Now apply this thinking to our cosmic horizon. Our entire observable universe is surrounded by an event horizon. Galaxies and their information are constantly crossing this boundary, disappearing from our causal reach. Does this mean information is being destroyed on a cosmic scale, violating quantum law? Or is it, too, being preserved? This line of reasoning leads to one of the most breathtaking ideas in theoretical physics, the holographic principle. It proposes that our three-dimensional universe, with its galaxies, stars, and us, might be a projection of information stored on its two-dimensional boundary, the cosmic horizon. Think of it like a hologram on your credit card. The flat, two-dimensional surface contains all the data needed to project a three-dimensional image. In the same way, the ultimate description of our reality might be written on the distant surface of our observable bubble. The edge of the universe would not be a barren wall, but the cosmic equivalent of a hard drive, storing the information for everything within. While this sounds like science fiction, it is a serious framework born from the mathematics of black holes and string theory. It suggests that the limit of our vision is not the end of physics, but its foundation. The true laws of the cosmos may not be written in the stars, but on the horizon we can never touch. The James Webb Space Telescope delivers breathtaking images of infant galaxies, but even its golden mirror has a finite reach. It captures light that has journeyed for over 13 billion years, showing us the universe in its formative youth. Yet this profound view represents only a fraction of our observable bubble. The telescope is an archaeological tool, digging through layers of cosmic history, but the deepest strata remain beyond its grasp. Our technological prowess is extraordinary, allowing us to build machines that function flawlessly a million miles from Earth. But it is ultimately bounded by the same cosmic rules that create the horizon. Each new observatory is a testament to human ingenuity, a leap forward in our ability to collect the faint whispers of photons that have traveled across the eons. Proposed future missions, like the Large Ultraviolet Optical Infrared Surveyor, or LUVOIR, envision a telescope with a mirror so vast it would need to be assembled in space, capable of directly imaging Earth like planets around other stars. These instruments will extend our vision further than we can currently dream, mapping the cosmic web in unprecedented detail, and perhaps detecting signs of biology on distant worlds. But they will all eventually face the same impassable wall. No telescope, no matter how advanced, can see an object whose light has not had enough time to reach us. They cannot peer beyond the particle horizon any more than a sailor can see a shore that is still over the horizon. This is not a failure of engineering, but a fundamental feature of our relativistic universe. Our quest to see the edge is therefore a race on two fronts. We are pushing the boundaries of technology, building ever more sensitive eyes to see further into the past, while simultaneously refining our theoretical models to understand what must lie in the darkness we can never illuminate. This duality drives progress, forcing us to be clever, to infer what we cannot observe, and to accept that some mysteries may remain forever just beyond the light. This intricate cosmic web is the largest structure we have ever mapped. It is not a random scattering of stars and galaxies. Instead, galaxies are gathered into immense clusters, which are connected by long, delicate filaments of dark matter and gas, creating a pattern that resembles a neural network on a universal scale. Between these filaments lie vast, empty voids, regions of near-total emptiness that can span hundreds of millions of light-years. This is the grand architecture of the cosmos, and it is our most important clue for understanding what lies in the darkness beyond our sight. We can only directly chart the portion of this web that lies within our 46 billion light-year bubble. Yet, the pattern we see is remarkably consistent in every direction we look. This observed uniformity is the bedrock of the cosmological principle, the idea that on the largest scales, the universe is both homogeneous and isotropic. It looks roughly the same everywhere and in every direction. This is a powerful assumption. It allows us to use the visible part of the cosmic web as a reliable sample. By studying the statistical properties of the filaments and voids within our view, we can create models that predict the structure of the universe far beyond our horizon. It is like being in a vast forest, but only able to see a few hundred yards in any direction. If the trees you can see are distributed in a consistent pattern, you can make a very educated guess that the entire forest, stretching for miles you cannot see, follows the same basic arrangement. Cosmologists do this with the universe. They run sophisticated computer simulations that start with the tiny fluctuations imprinted on the cosmic microwave background, and then let the laws of physics play out over billions of years. Gravity pulls matter into the denser regions, forming the web of galaxies we observe today. The stunning success of these simulations in recreating the web we see gives us tremendous confidence that the same physical processes are at work everywhere. Therefore, the cosmic web almost certainly does not end at our particle horizon. The filaments likely extend into the darkness, weaving through an infinite expanse, connecting galaxy clusters we will never witness. The great voids are probably even vaster than we can measure. This indirect exploration is a testament to the power of scientific inference. We are using the light we can catch to build a reliable model of the eternal darkness we cannot. This cosmic web, a tapestry woven from dark matter and galaxies, hints at a structure that continues indefinitely into the dark. Yet the threads of this tapestry could be spun from even more exotic materials than we have yet found. Among the most compelling candidates for the invisible substance holding the cosmos together are primordial black holes. These are not the stellar mass black holes born from dying stars, or the supermassive giants lurking in galactic cores. Primordial black holes are theoretical relics from the universe's first frantic moments. In the extreme heat and density just after the Big Bang, random fluctuations could have caused pockets of space to collapse directly into black holes. They could range in size from smaller than an atom to larger than a star, a hidden population woven into the fabric of reality from the very beginning. If they exist in great numbers, these ancient objects could account for a significant portion, or even all, of the dark matter that governs the growth of galaxies. We search for their faint signatures within our observable bubble, looking for the way their gravity might bend the light of distant stars in events called microlensing, or listening for the ripples they might create when they collide. But our searches have so far come up largely empty, placing strict limits on how many such black holes could be hiding in our galactic neighborhood. This, however, only deepens the mystery of what lies beyond. The rules of physics that allowed for their formation here would have operated everywhere. If our local universe seems to have a scarcity of primordial black holes, does that mean they are rare across the entire cosmos? Or is our observable bubble simply a quiet backwater, while the greater universe beyond the horizon is densely populated with these ancient gravitational ghosts? Their potential existence transforms the nature of the unobservable realm. The darkness beyond our horizon is not a featureless void waiting for galaxies to arrive. It could be a landscape already teeming with phenomena that are rare or absent in our own celestial vicinity. It might contain entire constellations of primordial black holes drifting through the eternal night, their presence forever undetectable to our instruments. This possibility adds a profound new layer to the cosmic frontier. We are not just missing more of the same. We might be missing entirely different chapters of the cosmic story, chapters written in the language of gravity alone. Our very existence might be the most profound clue to the nature of the unseeable cosmos. The fundamental laws of physics appear suspiciously fine-tuned for life. Alter the strength of gravity by a fraction, or tweak the force that holds atomic nuclei together, and stars would never form. Complex molecules would be impossible, and the universe would be a barren void. This cosmic coincidence demands an explanation. The Anthropic principle offers a startling answer, one that directly ties the scale of reality to the fact that we are here to observe it. It simply states that the universe we observe must be compatible with the existence of conscious observers. This sounds almost trivial, but its implications are revolutionary when applied to a cosmos larger than our observable patch. If the universe is truly infinite, or if it is part of a multiverse where different regions have different physical constants, then life will only arise in those rare, hospitable pockets. We do not live in a special universe fine-tuned just for us. We live in the only type of universe we could possibly inhabit. The edge of our observable bubble, then, is not just a limit to our telescopes. It is a biological horizon, marking the boundary of a region where the local laws permit our form of existence. Beyond that edge, the constants of nature could be radically different, creating realms of reality where matter is unstable, or where time itself flows in unfamiliar ways. This idea reframes our cosmic address from a random point on a map to a necessary location. We are not at the center of the universe, but we are necessarily in a place where the universe allows for centers of consciousness to emerge. The darkness beyond our horizon is not merely empty. It could be filled with universes that are, for us, unimaginable. Our understanding of the cosmic horizon has always been a story of receding boundaries. For millennia, the horizon was literal, a dome of stars that rotated around a stationary Earth. This was a small, knowable cosmos, with humanity comfortably at its center. The shift began when Galileo turned his telescope to the heavens, revealing moons around Jupiter and imperfections on the Sun. These observations shattered the perfect celestial spheres, suggesting a universe far more vast and complex than previously imagined. Then came Isaac Newton, who described a universe of infinite space, governed by universal laws of gravity. The horizon seemed to vanish, replaced by a star-studded void stretching forever in all directions. Yet this infinite universe was static and eternal, a grand stage that had always existed. The next great revolution arrived with Edwin Hubble in the 1920s. By measuring the redshift of distant galaxies, he discovered that they were all rushing away from us. The universe was not static, it was expanding. This single observation completely rewrote our cosmic address. It meant the universe had a beginning, a moment of creation we now call the Big Bang, and it instantly created a new kind of horizon, a temporal one defined by the finite speed of light and the expansion of space itself. Each of these paradigm shifts was initially met with resistance, forcing humanity to abandon a comforting, central position for a more humble and far more astonishing reality. This historical pattern suggests a profound lesson. Our current model of a finite observable universe, bounded by a cosmological horizon, is our best description based on the evidence we have. But history tells us it is almost certainly incomplete. Just as Galileo and Hubble could not have predicted the full implications of their discoveries, our current view of the horizon is likely a temporary frame, a picture that will be redrawn by the next great theoretical leap or observational surprise. The true frontier may not be a line in space, but the limit of our current imagination. This journey into the void forces us to confront the ultimate why. Why do the fundamental constants of nature possess the exact values that allow for galaxies, planets, and life? The strength of gravity, the mass of an electron, the energy of the vacuum, these numbers seem arbitrarily fine-tuned. Alter any one by a minuscule amount, and the universe would be a lifeless expanse of radiation or a swift collapse back into nothingness. The landscape of string theory offers a breathtaking, if speculative, answer to this profound riddle. As a leading candidate for a theory of everything, string theory attempts to describe all particles and forces as minuscule, vibrating strings. But this elegant framework comes with a staggering implication. The mathematics do not point to a single, unique universe. Instead, they describe an immense landscape of possibilities, a cosmic catalog of perhaps 10 to the power of 500 different potential vacuum states. Each of these states corresponds to a stable universe with its own unique set of physical laws and constants. Our universe, with its particular gravitational strength and particle masses, is just one entry in this unimaginably vast catalog. The unobservable realm beyond our horizon, then, may not be filled with more of the same. It could be a multiverse, a cosmic foam where each bubble is a separate universe with its own distinct physics. In some bubbles, gravity might be so strong that stars form and burn out in an instant. In others, the forces may be too weak for atoms to ever bind. Our universe is not special. It is simply one of the rare, habitable pockets where the local laws accidentally permit our existence. This transforms a philosophical mystery into a potentially scientific one. The question is no longer why our universe has its specific properties, but what is the statistical distribution of universes across the multiversal landscape? We find ourselves in a universe that allows for observers because we could not find ourselves anywhere else. This represents a radical shift in the goal of fundamental physics. The focus moves from discovering the one true set of laws to understanding the probability distribution of laws across the unobservable whole. It suggests that the ultimate answers we seek may be locked away, not just beyond our telescopes, but in the statistical fabric of a reality we are forever barred from directly exploring. This cosmic isolation is not just a physical reality but a deeply personal one. It forces us to weigh our brief, brilliant lives against the silent, eternal expanse. We are temporary inhabitants of a tiny rock, orbiting an average star in a galaxy that is just one among countless others, most of which are now forever beyond our reach. This realization can feel crushing, a lesson in ultimate insignificance. Yet, it can also be strangely liberating. Every worry, every conflict, every triumph in human history has occurred within this single, shimmering bubble of reality. All of it is cosmically local. This perspective does not diminish our experiences, but rather frames them as precious and unique within our island of the knowable. The ethical question then becomes not whether we should explore, but why we must. If the final answers are permanently hidden, is the scientific quest a form of cosmic folly? The value may lie not in the destination, but in the journey itself. Each new discovery, from the first telescope to the latest gravitational wave observatory, is an act of defiance against the darkness. It is our way of mapping the library we are born into, of understanding the local rules of our existence, even if we can never leave to see the greater mansion. This pursuit is a fundamental expression of what it means to be human, to be curious. The light from those distant, fading galaxies tells a story of a universe that is vast, beautiful, and largely unknowable. Our act of listening to that story, of trying to understand our place within it, is what gives our fleeting moment in the cosmos its profound meaning. Even as we map the cosmic web with increasing precision, new eyes are being designed to see what our current telescopes cannot. The Laser Interferometer Space Antenna, known as LISA, represents a completely new way of observing the cosmos. Instead of collecting light, it will listen for the faint ripples in spacetime caused by the most colossal events in the universe. Imagine 3 spacecraft flying in a perfect triangle millions of miles apart, connected by laser beams. When a gravitational wave passes through, it will minutely change the distance between the spacecraft, and LISA will detect this incredibly subtle stretching of space itself. This technology will open a low-frequency window on the universe, allowing us to hear the mergers of supermassive black holes and, most tantalizingly, the primordial vibrations from the era of inflation. These waves would be a direct signal from a time before the cosmic microwave background, a whisper from the very instant of creation. Alongside LISA, a new generation of telescopes will stare at the afterglow of the Big Bang with even greater sensitivity. These instruments will scour the cosmic microwave background for a specific, faint pattern, a telltale swirl imprinted by those first gravitational waves. Finding this signature would be like discovering the original fingerprint of the inflationary burst, confirming our deepest theories about the universe's violent birth. No single instrument will ever allow us to peer beyond the absolute horizon, but together, they will paint an exquisitely detailed portrait of its inner surface. They will tell us more about the conditions that forged our cosmic bubble, the physics of the first moments, and the very nature of the boundary that defines our reality. This relentless effort is a testament to our species' unique drive. We are building machines not to see the other side of the wall, but to understand every grain and imperfection on our side, using the faintest echoes to reconstruct a history we can never directly witness. The equations that map this cosmic boundary are not arbitrary guesses. They are precise, predictive tools born from Einstein's theory of general relativity. At their heart are the Friedmann equations, a set of mathematical relationships that describe how the universe expands over time. Think of them as the cosmic equivalent of a speedometer and an odometer for the entire cosmos. They do not just tell us the universe is expanding, they tell us how the rate of that expansion has changed from the Big Bang until today. To find the distance to the particle horizon, the edge of what we can see, cosmologists perform a specific calculation. They integrate or add up all the tiny increments of distance that light could have traveled during each fleeting moment of the universe's 13.8 billion year history, while accounting for the fact that space itself was stretching during the entire journey. It is like calculating how far a car has traveled on an expanding rubber road where the car is light, and the road is the fabric of spacetime. This calculation yields that seemingly paradoxical number, the 46.5 billion light-year radius of our observable universe. The mathematical framework also defines the more subtle cosmological horizon, the future boundary of what we will ever see, by projecting the accelerating expansion driven by dark energy forward in time. This is not abstract number crunching. These equations made a spectacular prediction. They forecast the existence and the specific temperature of the cosmic microwave background long before it was accidentally discovered. The math told us what to look for, and the universe confirmed it. So when we speak of the edge, we are not describing a vague idea. We are pointing to a line defined by the rigorous, tested language of mathematics, a line that continues to shape our understanding of the cosmos. This single bubble of observation creates a profound scientific dilemma. We are trying to understand the entire cosmos, but we are trapped inside a single sample, a lone data point. This is the problem of cosmic variance, a unique and frustrating limitation in cosmology. In any other science, if you want to know the average properties of something, you study many examples. To understand the average height of a tree, you would not measure just one tree in a forest. You would measure hundreds to get a reliable average. But we cannot do that with the universe. We have only one universe to study, or at least, only one observable patch of it. So when we measure something on the very largest scales, like the grand sweep of the cosmic web, we face a fundamental question. Is what we see truly typical of the universe as a whole? Or is it just a statistical fluke, a peculiarity of our local neighborhood? A key example of this uncertainty is found in the cosmic microwave background itself. This ancient light is incredibly uniform, but it does have a subtle asymmetry, a temperature difference between one side of the sky and the other, known as the dipole. We have long assumed this is due to our own motion through space, a Doppler effect from the Earth's journey. But what if part of that signal is not generated from within our bubble? It is possible that the gravitational pull of an unimaginably vast supercluster, a concentration of mass so enormous it lies beyond our cosmological horizon, is tugging on our entire local group of galaxies. This external structure, forever invisible to us, could be imprinted on the oldest light we can see, warping our measurements from the outside. This means that some of our most fundamental observations about the universe carry an inherent, unsolvable uncertainty. We can never know if our cosmic backyard is average, or if we reside in a particularly dense or particularly empty suburb of the greater cosmos. Every calculation we make about the whole universe is therefore a statistical inference, a best guess based on a sample size of 1. The edge of our vision is not just a barrier to seeing more. It is a barrier to true certainty, forcing cosmologists to become experts in probability, forever wondering what lies hidden in the statistical noise. This cosmic cage, defined by the speed of light, seems a world apart from the fuzzy, uncertain realm of quantum mechanics. One governs the vastness of galaxies, the other the dance of subatomic particles. Yet these two pillars of physics are not separate. They collide in a spectacular way at the very boundary of our vision. The immense structures we see today, the great cosmic web of galaxies, owe their existence to the tiniest of quantum events. In the first fleeting moments of inflation, empty space was not truly empty. It was a seething quantum foam, where pairs of particles and antiparticles spontaneously flickered in and out of existence. As the universe underwent its hyper-fast expansion, These microscopic quantum fluctuations were stretched to astronomical proportions. A tiny region of slightly higher density, born from a random quantum wobble, was inflated to become the seed for an entire galaxy cluster. The grand architecture of the cosmos is, therefore, a quantum signature written on a cosmic canvas. The universe began with a whisper of quantum uncertainty and amplified it into a roar of galactic formation. This means that when we look at the largest scales, we are indirectly observing the effects of the smallest. The edge of our observable universe is not just a barrier, it is a fossil record of quantum history. This profound connection hints at an even deeper mystery, one that challenges our very understanding of reality. If the entire contents of our universe were born from quantum data, where is that data ultimately stored? The holographic principle provides a radical answer. It proposes that all the information describing the three-dimensional world within our cosmic horizon, every galaxy, every star, and every one of us, is actually encoded on its two-dimensional boundary. Think of it like a movie. The rich, three-dimensional world you see on the screen is projected from the flat, two-dimensional data on the film reel. In this cosmic analogy, the film reel is the spherical surface of our observable universe, and the movie is everything inside it. This is not just a poetic idea, but a serious mathematical consequence of uniting quantum mechanics with gravity. The physics that describes a volume of space may be equivalent to the physics that describes its surface. This suggests that the ultimate frontier of knowledge is not a distant point in space we must travel to, but the very limit of our perception itself. The key to unlocking the secrets of the quantum world might not be found by looking inward, toward smaller and smaller particles, but by looking outward, toward the edge of everything we can see. The horizon is not a wall, but a screen, and the universe we experience may be the projection. These theoretical doorways through space-time are not just science fiction, but mathematical solutions to Einstein's own equations. A wormhole, for instance, is like a cosmic shortcut, a tunnel connecting two distant points in the universe. If one entrance were placed just inside our cosmological horizon and the other far beyond it, we might, in principle, send a probe through. Similarly, an Alcubierre warp drive proposes a way to cheat the speed of light not by moving through space, but by contracting the space in front of a ship and expanding the space behind it. The vessel would surf on a wave of space-time, never locally breaking the light speed limit, yet arriving at its destination faster than a beam of light traveling the normal route. The catch, and it is an immense one, is the energy required. To warp space-time in such a dramatic way would demand negative energy densities or the mass energy of entire stars, putting these ideas firmly in the realm of far future speculation. They are reminders that the laws of physics, while strict, may have loopholes we have not yet learned to exploit. A more tangible, though still incredibly challenging, path forward lies not in traveling to the horizon, but in finding better messengers from it. Gravitational wave astronomy is in its infancy, but future observatories could detect waves from the very first seconds after the Big Bang, from a time before the cosmic microwave background was set free. Neutrinos, those ghostly particles that barely interact with matter, streamed through the opaque early universe long before light could. A perfect neutrino telescope, an instrument of almost unimaginable scale, could capture these relics and peer back to a time even closer to the very beginning than we ever thought possible. These are not technologies for our generation or even the next 100. They are thought experiments that test the limits of physical law. They ask a profound question: is the horizon truly a permanent prison, or is it merely a puzzle we have not yet learned how to solve? The value lies not in a guaranteed escape, but in the act of pushing our imagination to its absolute limit, exploring every conceivable avenue in our eternal quest to see beyond the veil. This invisible frontier has seeped into our collective imagination, becoming a powerful modern myth. Science fiction has long grappled with the implications of a universe we cannot fully explore. Countless stories feature generation ships, immense vessels where entire civilizations live and die during journeys lasting millennia, all aimed at reaching galaxies that remain, for now, mere specks of light. These narratives are not just about adventure. They are profound meditations on our place in the cosmos. They ask what kind of society would commit to a project whose completion no living soul will ever witness, a testament to hope against the backdrop of cosmic isolation. The Horizon reframes the classic trope of endless exploration. For centuries, human stories followed a pattern of outward expansion, of pushing back the map's edge. But the cosmological horizon introduces a different kind of story, one of tragic limitation. It suggests that the final frontier might not be a challenge to be overcome with better engines, but a permanent boundary written into the laws of physics itself. This shifts our vision of the future from one of galactic empire to something more poignant, and perhaps more realistic. Our ambitions as a species are now framed by this cage of light. Will we content ourselves with cultivating our own galactic island, knowing that most of the cosmic ocean is forever out of reach? Or does this very limitation give our local endeavors a new and profound meaning? The horizon becomes a symbol not of failure, but of focus, forcing us to consider the value of the knowledge and the beauty we can access, rather than lamenting what we cannot. It mirrors a fundamental human experience, the realization that every life and every civilization operates within its own finite sphere of possibility. The universe's greatest lesson might be about finding infinity not in boundless space, but in the depth of our understanding of the world we are given. The cosmological horizon is far more than a simple line in space. It is a dynamic, evolving boundary that forces us to distinguish between what we can see and what we can know. Our journey has revealed that this edge is not a wall but a complex phenomenon, born from the finite speed of light and actively reshaped by the mysterious force of dark energy. It is a filter, a jailer, and a profound historical record all at once. This single concept ties together the entire cosmic story, from the inflationary burst that smoothed the infant universe to the faint whispers of gravitational waves that may one day reveal its first moments. The horizon is the reason we can speak of a multiverse, an infinite cosmos, or a cyclical existence. It is the blank canvas upon which we project our most ambitious hypotheses, precisely because it denies us direct observation. This fundamental limitation has paradoxically become the greatest catalyst for theoretical physics, pushing scientists to ask questions that would have seemed like pure fantasy just a century ago. Are the laws of physics truly universal, or are they merely the local bylaws of our isolated bubble? Is information truly lost when a galaxy crosses the horizon, or is it preserved like a cosmic hologram? The horizon does not mark the end of science, but the beginning of its most profound chapter, where data meets deep speculation. It stands as a permanent reminder that the universe is under no obligation to be fully comprehensible to us. Yet, our relentless drive to peer into the darkness, to decode the whispers from the edge, is what transforms our cosmic isolation into a story of endless curiosity. This cosmic horizon, then, is the ultimate teacher of perspective. It shows us that our most profound scientific truth is the acceptance of a fundamental limit. We are confined to a single, shimmering bubble of reality, a grand theater where the entire drama of human history has played out on a tiny stage. Yet, this very limitation is what fuels our greatest ambition. The drive to map this bubble, to understand its every law and listen to its faintest echoes, has given us relativity, quantum mechanics, and telescopes that see back to the dawn of time. The horizon is not a dead end for science, but its most fertile ground. It forces us to be more clever, to ask deeper questions, and to recognize that the universe's greatest secrets are not always hidden in the light we can see, but in the careful study of the darkness we cannot. Our place in the cosmos is not one of central importance, but it is one of unique opportunity. We are the part of the universe that has become self-aware, capable of looking out from our island and pondering the infinite ocean. While we may never sail upon it, the very act of charting our own shores, of understanding the nature of our cage, is a monumental achievement. It transforms our fleeting moment under the stars into a chapter of cosmic self-discovery. So the next time you look up at the night sky, remember that you are not just seeing stars. You are gazing at the edge of the known, a boundary that invites us not to despair, but to wonder. What do you think lies in the great beyond? Share your thoughts on this ultimate frontier.